way, we see globular cluster, and these are really relics of star formation happening many gigayears ago. So this is, of course, its own field on its. So you can look directly into single stars. You can probe mass function down to brown dwarf regime in star cluster. With Gaia, we are actually tracing back where the stars are forming and finding beautiful star cluster complexes. But today, for the rest of the talk, I will use the word young star cluster to actually grasp mostly of what you see here between Westerlund and Pleiades. And then a globular cluster is the term that I will use for old ancient star cluster. What we see essentially is that they are gravitationally bound, so stars actually stay together, move together in the galaxy. Their sizes are really compact, between 1 and 10 parsec. We find them in different mass ranges. I think the most massive one is about 10 to the 7, 10 to the 8 in the local universe. So we know it's a star cluster because it's 10 parsec across and is found in post-starburst events. So it has survived already 100 million years there. And of course, we have this intuition, the globular cluster have survived already a Hubble time. So when we move in the local universe, essentially this is M83, it's 5 megaparsec away. We see all the phases from their formation, interaction with the immediate ISM, the H2 regions, and then we see them evolving in the disk. And this is the view that I would like you to keep during the entire talk, because we are not going to resolve stars within star cluster, but we use them as a tracer of star formation in galaxies. So I think also you are, like if you think of M82, right, with this beautiful outflow on the disk, we are all aware that this outflow is coming from a region that is very compact, a few hundred parsec, where a cluster of 10 to the 5, 10 to the 6 solar masses have formed. And we see this ubiquitously where we see outflow, and we can look inside the galaxy and resolve the stellar population. We see that the star cluster, for even in low mass dwarf like SBS 0335 and other blue compact galaxies, that essentially the stellar cluster within these galaxies have been able to blow the ISM of galaxies and create large outflows, galactic scales outflows, and large halo of ionized gas around these galaxies. So when we try to study feedback in star cluster, we can do it in different ways. In particular, I would like today to show you some results from COS, so far UV spectroscopy analysis of star cluster. We are looking within local galaxies. So here you see the sample. We are sampling dwarf galaxies, paragalaxy, and the COS aperture is giving us the spectroscopy of the cluster. So this is the CLUES project. And here you see Mattia, who has recently defended this PhD thesis between me and Matthew Hayes. So we looked at the star cluster within the COS aperture. Here you see a zoom in. You see the cluster in the center. We get the fantastic far UV spectroscopy from these objects. And you see, probably not in this view, but believe me when I tell you that there is a lot of information. In particular, when we study cluster feedback, we focused on the line absorption lines that will be produced by the ISM along the line of sight from the UV light of the cluster. So when we do that, we are looking at an absorption line where we find where is the static component of the gas, which is in front of the star cluster, and the outflowing component, in this case, is the orange drawing here. So when we measure outflows, we measure how much is offset the gas from the thermal velocity, that is 0, right, the static component. And what we see, essentially, we can determine the energetics in the outflow, is that these velocities are essentially as a function of cluster age. You see here, it's a bit uncomfortable. Okay. So what you see here, we use lines that are either produced by ionized gas or neutral gas. and we plot the age of the cluster. And what we see is that there is not a direct connection with age. It looks almost that there is kind of a coupling, but then it disappears very rapidly. So what we think is causing this effect, the lack of correlation between the outflow velocity produced by the feedback of the cluster and the age of the cluster, is the coupling efficiency. So if you don't have full coverage of the gas is fragmented, of course, around the cluster. Then when you accelerate this gas, you don't give 100% of power from the cluster feedback. But what we see, and this is with some correlation statistics here plotted, is that this outflow velocity seems to couple better with cluster mass, so with the amount of feedback produced by the star cluster. And in fact, we are able to estimate the coupling efficiency directly using the outflow velocity of the gas, so we can estimate the mechanical energy, the kinetic energy in the outflow versus the outflow produced by the mechanical energy produced by the cluster population, the stellar population in the cluster. And we see this, that the coupling efficiency is not 100%. When we compare this outflow velocity with galaxies, because this is on a field essentially, when you study how the energetics of the star formation within galaxy create galactic scale outflow, you see the galaxy are these red symbols, so black open symbol or thick symbols. They scatter in a star formation rate via outflow velocity, and the star cluster population sits right here. So we find the similar slopes, of course, not of course, with a lot of scatter, of course. The scatter is due to the way there is much more physical information that is hidden in the scatter in this plot. So it's not a simple relation between star formation rate and outflow velocities. But then when we remove the dependency of size, so we collapse and we divide by the star formation area, so we are looking at star cluster and galaxy, the difference, the offset between the samples of star cluster and galaxy is removed. So essentially, star cluster, you can imagine the mechanical energy produced by star cluster is a normalization of what happens in the galaxy when you have hundreds of star clusters paired up together. So I hope this is one important information, because when we will look then at other galaxies at high redshift, it's important to look at what is happening within galaxy if we want to understand their outflows. Then other information that I think are useful for you for during this talk about star cluster population is that how much star formation in galaxy takes place in star cluster. And this we have been trying to derive these values using different galaxy properties. And in general, what we see, so this we call it gamma, cluster formation efficiency, is that this fraction changes as a function of star formation rate density in the galaxy. So more dense is piled up the gas, more star formation is taking place in star cluster, which then connects again to the ability of launching outflow in galaxy, or why we see outflow in starburst galaxy. So here you see an example again. This is one of the galaxies I was showing before with a very large outflow surrounding from MUSE data. And then you see here the mergers between Lurg's galaxies. So these are the most extreme star-forming environment. Have a very high cluster formation efficiency. While when we move down to spiral galaxy or dwarf galaxies here, we go down and the cluster formation efficiency goes down to a few percent. And finally, one last introductory slide is about the mass function. And I know you all know that the mass function of a star cluster is a power law. But actually what we have been doing in the last years is to determine what is the high mass and shape of the mass function. So what we see here, essentially, there is a black line underlying the blue, is that the shape of mass function in local galaxy is not a pure power law, because otherwise the black line should follow the red distribution here. It's a Schechter function type with a break, an exponential break at the high mass end. They're characterized by this truncation mass, MC, this characteristic mass. So this is important because then when we try to see how many massive clusters you are producing in a galaxy, what we see is that actually the number of very massive cluster is around this Schechter value, the characteristic mass. So it's significantly lower than using a power law. And this has important implication when then we try to derive the feedback by looking at star formation rate in galaxies, for example. And in fact, what we see, this is one of the final relations, is that this characteristic mass is scaling with star formation rate density. So we know that as galaxies become higher, form cluster faster and in a more compact fashion in galaxies, they will form a more massive cluster. And here again, you see in local galaxy, we find this very massive cluster in merger or starburst, while spiral systems are sitting here. So, and then finally, the last piece of the puzzle is a globular cluster. And here you are seeing a low surface brightness deep image of M33, M31. And all the streams around M31 are connected to actually globular clusters. So we know the globular cluster in halo of massive galaxies in the local universe are coming in via accretion of satellite galaxies. And in fact, if we look at our own Milky Way, we see enrichment. If we look at the metallicity of globular cluster, we see that there is a trend with the metallicity and age of globular cluster, where we think that these objects here are those formed in situ in our Milky Way progenitor. And these are streams of globular cluster are coming in via satellites. The mass function of globular cluster is different from what we see in the local universe. So we all know that as a turnover, and this turnover is almost universal. In fact, the globular cluster luminosity function have been used to estimate distance of galaxies, for example, in the past. And then the globular clusters show chemical patterns which we don't see anywhere else in the local universe. In particular, here you see that there is a correlation between sodium and nitrogen, and the anti-correlation between oxygen and the sodium, which corresponds to an anti-correlation also with nitrogen and oxygen. And this becomes very interesting when we look then at high redshift with the spectroscopy from JWST. And finally, we are seeing intermediate mass black hole within globular cluster around the Milky Way, which is also an interesting detail that comes up later at the end of the talk. So today, of course, I will give you an hint of what we know about star cluster in the local galaxy, but I know in my abstract I was talking about high redshift. In reality, what I'm gonna do is giving you a bit more of what we are doing with JWST in local galaxies and in specific phases of cluster formation. And then we will move into the high redshift. So bear with me for another 5 minutes, and then we will leave the local universe forever. So, and essentially, what we have been missing until now in all this study is the emerging phase. When clusters are deeply embedded, they are forming within the core of giant molecular clouds. And then we know that eventually their feedback is destroying the clouds, it's creating the H2 regions, but we don't see this phase And we don't know actually very well the time scales, because if you look at simulation, they depend on the way you describe your feedback, the star formation efficiency. I look at you, I know that this is what the people do when they do simulation, right? You assume star formation efficiency, you assume, but in reality, observation from real data will help. So let's look at the question, how long does it take for a star cluster? And I talk about star cluster telling clustered star formation, because we know that turbulence is creating these clustered regions where stars are forming. So we are looking at early stage, usually with ALMA, we look at this dense cloud, and we know that they are collapsing or in a stage that they will start collapsing. Then we know that magically, not magically, but within them, we have stellar cores, stars start to reach the main sequence, they start to ionized, but they are still deeply embedded, and they are surrounded by a photodissociation region with different conditions from H2 region. So you see here, temperature and density are changing dramatically as we move away from the stars which have just reached the main sequence. And then what we have been looking a lot with the MUSE, JWST, all the IFUs data, essentially all the way we can probe optical wavelengths is this phase, when we see the cluster population, the stars within the cluster, and we can look at the H2 region around the cluster. This evolution is really fundamental because essentially the time scales that it takes to destroy the dense gas around the stars will set the star formation efficiency of this region. It will set the time scale for molecular cloud disruption. And once you open channel and these regions fragment, you start to inject energy and momentum in the ISM. So we proposed for cycle 1, FEAST, that stands for Mapping Stellar Feedback in Emerging Extragalactic Star Cluster. What we did is essentially to look, first of all, thanks to the team, because it's not a single person job. It takes actually a lot of people to do and to analyze and understand the data set. Here you see one of the FEAST galaxy M51 in the images. So the FEAST project consists in a combination of broadband and medium narrow bands that sample hydrogen recombination line and pH emission in a sample that goes from 1 to 7.8 micron. So we sample the pH at 3.3 and 7.7 emission. And we have done that in galaxies that are within 10 megaparsecs. So we know we are going to resolve down to 10 to 1 parsec scale even. We have a spiral galaxy with different dynamics. We see pure spiral. We have a barred system, M83. We have M51, where the spirals are tightly winded due to the interaction with the companion that is not showing in this image. And we have also dwarf galaxies. So what we are learning, this is a view of the FEAST galaxies. Essentially, we are going and finding this embedded star cluster, and they are here projected with the contours, where in green we show the 3.3 pH emission very extended. It extends much farther than the H2 regions that are instead co-spatial with where we find the young star cluster, the embedded objects. And this here you see in the contour are giant molecular clouds, much lower resolution, but still we see that most of the embedded star cluster we extract are associated with dense molecular clouds. So they are still embedded, they are still forming stars. The color here stands for different classes. So you see what we call EYSC1 are deeply embedded objects that still have a pH associated with them, while the EYSC2 have already lost their pH. So we are looking just at normal H2 regions, as we have seen before. And then we find also a class of objects that we call the pH peaks. We don't know what they are. We see them also in the 7.7. We think they may be star clusters that do not have massive stars, so do not ionize. We don't see them in bracket alpha, Paschen alpha. So Actually, in August, we got spectroscopic data, and we are able to see a difference. This is a spectrum of a young star cluster 1. You see essentially that there is a bump. This is hot dust emission over under bracket alpha, and the 3.3 pH emission. We see a forest of lines, which actually are H2 lines. We are trying to look at them. And we see, of course, also all the hydrogen recombination lines that are present in this spectra. And here you see a young star cluster where we have EOSC2. So all the hot dust component has disappeared. The pH is there, but actually we haven't done local sky subtraction. So it's possible that it's coming from diffuse pH in this region. And then we see the prominent line that are left are hydrogen recombination lines. So spectroscopy essentially confirms our way of detecting this object. Here you see in broad JWST colors, and here essentially we are sampling the continuum, stellar continuum, and the hot dust emission. And you see here instead we are stellar continuum and pH emission. And essentially this sequence of emerging cluster lose gradually their pH, their PDR association within the aperture, and then move where they are supposed to be when they are young star cluster. And I think I will skip the next slides. But essentially the color of this extracted source coincide with the YSO class 1 and 2 in the Milky Way. Interestingly, when we look at the shape of the PDR, where the star clusters are sitting, so here you see this is Paschen alpha is always peaked. So we are looking at compact object, H2 regions, but the pH is changing in morphology. And Alex, a grad student in Stockholm, he has actually studied their light profiles. And what we see is that the PDR traced by pH essentially is changing, is becoming like a donut shape. And you see here the surface brightness profile are changing while the Paschen alpha is still peaked in the system. So this evolution coincides also with the ratio of pH, which is suppressed with respect to model where there is a mixture of neutral and ionized pH. And here you see these are ionized pH prediction, and these are a mixture. So when we look at a scale of 10 to 20 parsec, we are seeing already what we think we are seeing is pH destruction. But then curiously, it doesn't matter if we look at compact pH regions or open donuts pH region, the ratio in these two pH tracer is still the same. So what we see essentially is that both, when we use the age of the star cluster within the region, is that both pH are disrupted with similar rate. So the mechanism that is disrupting the neutral pH, the 3.3 micron, is similar to the one that is disrupting the mixed one at 7.7. And that's why the ratio stays constant. Okay, so at the end of this study, I will show you just a few hints. What we see is the emerging phase take up to 6 million years. And we see a very embedded phase where we don't find the Paschen alpha bracket alpha very fast. So this happens really fast that main sequence stars start to ionize the regions. And then this emerging phase takes roughly 3 million years, 4 million years for the PDR to be destroyed. And then finally, we are in these regions where clusters start to be visible in the optical, and we see the classic H2 regions. Okay, so I will skip. This is the summary of essentially what I just said in that. And we are moving now for the last half of the talk to high redshift, because actually with JWST, we can look at high redshift, we can look within galaxies. So here the question that I'm posing to you is when did the first star cluster form? So this is a work that has been done in collaboration with Adelaide Clessans, who is still in Stockholm, but is soon moving to Lyon. And then other people, Mirka, especially Mirka, Matteo, Johan, they've helped a lot in the analysis that I'm gonna show. So with the AGST, we have been able to look at galaxy up to redshift 6, let's say, and especially in their UV lights, we have seen the galaxy are losing the morphological classification. And what we have learned essentially with the AGST study, because AGST was the only one that allowed us to reach the highest spatial resolution at this redshift, is that these disks are dominated by stellar clumps. So now we are looking at scale of roughly kiloparsec, half kiloparsec scales, and that disks seem to actually completely disappear when we were looking at the UV light at redshift 2. So beyond redshift 2, there was no anymore. So disks are not in place yet. And to explain clumps, then we know there have been out-tumor instability consideration to make. So these are thick disks. They are very gas-rich, and they essentially fragment on galaxy scale. And that explains why you can form clumps of this size. Of course, we already before JWST, we knew that we could use lensing to magnify the galaxies. And this has already been done in studies. So we have been able, in some cases, to zoom into galaxy and look directly into the light. And I think one of the main results from JWST studies is that these clumps that we see in the field are actually resolved into objects that become star clusters at tens of parsec sizes. When JWST gave us the first early release image, I think everyone was essentially surprised to see these galaxies, but especially here, I would like to point out the sparkler. It's at disk ratio 1.4 with the globular cluster already in place. And this was a big, coming through. We knew the globular cluster at cosmic noon should already be surrounding galaxies, but this was the first time we were seeing them. So together with Adelaide, we have been actually looking at clumps in JWST images. And what we do, this is an example. Here you see a galaxy where there are little dots in it. And then we have created a fit the light distribution here. And we have created a model. We have subtracted. Essentially, we have removed the diffuse light of the galaxy. This model is very important because it's giving us the lens correct sizes and fluxes of these clumps. And therefore, we can build SED distributions, so spectral energy distribution in JWST bands to study the physical properties of this clumps cluster. That we are looking at cluster, we are reaching the regime of star cluster. It was already clear from this early study that we performed. So here you see in MAX 0723, we find stellar clumps in the region of 10 parsec, and then we find a population of stellar clumps down here that reach down to a few tens of parsec, 100 parsec. So when I think of the study we did, I would like to show especially the sparkler because there was a lot of work done. And here you see all the clumps that we could extract around the sparkler. And now the dots are color-coded according to the age of this object. And we see essentially that some of them seem to be really old. If we use essentially, okay, this is really, we are looking at the sparkler here, but some of these globular clusters seems to have been forming in a much earlier universe around redshift 9 or higher. If we looked at where the clumps were sitting, especially this cloud, this is the very old globular cluster, are sitting here. And depending which model you use to fit them, they could be metal-rich young or metal-poor and old. So when at the end of 2013, essentially, one more thing, and I will move on, is that this globular cluster or proto-globular cluster or objects surrounding the sparkler are gravitationally bound. So we know that their ages are long enough that they've been there more, so a lot more than their crossing time, right? If you have stars ages are all younger than crossing time, then it means it's expanding. If ages are higher than crossing time, we know the stars are staying bound in the star cluster. So we know that we were looking at a bound gravitationally cluster, but then in the literature, there were different results. And essentially, from the analysis we put out, we found this blue distribution of dots, while another work suggested that they were old and metal-rich. And essentially, when compared to the cloud of the Milky Way globular cluster, this is metal enrichment versus age of the globular cluster in the Milky Way. It was weird that this galaxy seems to have only metal-rich globular cluster. So what we did, we went and fitted actually this cluster, globular cluster redshift 1.4 using the same tool that we use for redshift 0. So this is a Bayesian code where we assume flat prior in age, mass extinction, metallicity. And what we find for this object essentially is that there is not a convergence in the fit, and that is what caused the difference in different results. We can see, for instance, that they are metal poor, but we don't know how metal poor. And we can see that they are old, but we don't have a really good constraint on the age of this object. And this is for both photometries and team analysis. So when we do that, and we use all the photometry, we see a cloud that is here with the large uncertainties. We know that these are old and metal poor, and there is a kind of enrichment going on that we expect. But we cannot do better than that because data are not deep enough, unfortunately. So here you see then what can we do? For instance, we can use simulation and try to understand what will the sparkler become at redshift 0. And what we see is that we will end up with a galaxy that is roughly between 10 to the 9 and 10 to the 10. So it's going to be a disk like M33 at redshift 0. So, but now we are looking also at, with JWST, we open kind of the horizon, and we are looking at the optical restframe of galaxy. With JWST, we were focusing on the UV, while we looking at the optical is actually telling us the galaxy and disks are in place much earlier. Okay, so that is very important, because then what it means is that if the tumor stability theories work for this cosmic noon, then we expect to see clumps all the way to redshift 6. And in fact, this is what is happening. So we have been looking now more recently to about 2744. This is uncovered data that people here have been working on and are part of, together with the mega science observation. So we have a suite of almost 20 web filters where we mix broadband and medium bands. And this is really a game changer for analysis of clumps, because this is a beautiful image of uncover. But essentially, when we have a medium band and broadbands, we can actually go and study the properties of clumps with high precision. So here you see the sample we have been looking at is roughly 500 galaxies that have a magnification between 2 and 100. 40% of this sample has been confirmed spectroscopically so we know the redshift with high precision, but actually with the medium bands, the redshift of all the sample is quite tight, and so the variation are 0.1. And for the first part, sorry, we will look at the clumps that are between in this redshift range. So where we see here the number of clumps as function of redshift of the galaxy. And this is the type of numbers we have in the galaxy we are looking at, up to redshift 6. So this is an example of the SEDs of clumps. You see essentially that when the medium bands are available, we are able to see emission lines. So we have a tighter constraint on the physical properties of the clumps. And what we do with that is that, for instance, we see as a function of size, an increase in star formation rate density of clumps as we go to higher redshift. It seems that there is an evolution. So here you see star formation density is increasing in clumps. So galaxies are becoming, clumps in galaxies are becoming highly star forming as we move close to redshift 5 and 6. And something important to notice is that this is completeness. This lower limit here is produced by completeness, but the upper end is significant, the change. We don't see at redshift 1 clumps that reach this star formation rate densities at redshift 5. And also here you see the stellar densities are significantly high. So this, imagine the clumps, we are looking at the sizes on average of 150 to 100 here. And what we see is that they have a stellar density that can reach a star cluster in the local universe and globular cluster. So these are the two lines for stellar density. So we are looking at very highly dense objects, stellar complexes. We see also that if we look as a function of redshift, clumps are becoming on average increasingly older within their galaxies. So we see that essentially clumps in galaxy at redshift 1 are significantly older than clumps in galaxy at redshift 5. And this is due to the evolution in galaxies. So galaxy disks are forming, are growing in mass, and their clumps are surviving for a certain time scales within them. They dominate the mass of the galaxy, the clumps. We see that they can be up. So the central clumps are actually very massive. So a few percent of 10% of their galaxy mass. And this is very important because essentially these are the proto-bulge forming in galaxies. And again, this is the star formation rate density that we have already seen. So in general, the trends, the regions that we can resolve better than a few tenths of parsec have a very high star formation rate density. They have increasingly young ages, dominate the mass of their disk, and have high stellar density. These are the regions where proto-globular clusters are forming, but we cannot see them. But we can see essentially this is indicative the globular clusters are forming in extreme environment. And finally, I think this is really important, is that the mass function of clumps at different redshift follows a power law. Essentially, in this redshift range, we are seeing fragmentation happening in disks because the power law -2 is produced by turbulence, essentially breaking down the ISM and creating overdensity that collapse. So I think this is interesting. There was not enough number to look at the mass of galaxies, but we are now moving in the last 7 minutes to 6 minutes to actually looking really at proto-globular cluster. Now we are reaching the reionisation era. And when we look at galaxy reionisation era, what we see is that they are extremely compact. Imagine that there are galaxies that have just 100, 200 parsec across as we move to high redshift. This galaxy, I think, is a record breaker, 16 parsec in all and 10 to the 7 solar masses. So galaxies are becoming extremely compact. If you remember at the beginning of the talk, we know from local universe, when you have a very compact star forming episodes, it's for sure that you are forming star cluster within them. galaxy seems to be bursty. They go and grow their mass in this period of cosmic evolution via bursty phases. And they produce a lot of ionizing radiation. This is how we think they are essentially driving reionization in the universe. So when we looked at the sample at this redshift, we are going down dramatically in numbers. We are looking roughly at 95 galaxies, but the number of confirmations spectroscopically is much higher. So what we see essentially is that the stellar mass of clumps is going up because we are seeing essentially only the high mass end of these clumps, but clumps are becoming really young. So now we are reaching objects of 10 million years on average within galaxies. And then the density are are staying very high. So as I said before. Then when really now in a few objects, we are able to stretch with lensing to parsec scale. What we see, for example, this is redshift 6, the sunrise arc. We find the star cluster that are already evolved and they show a Balmer break in their light. So we are sure that their ages are older than 10 to 30 million years. And they are gravitationally bound because their sizes are a few parsec scale. Look at the stellar density of this object in this galaxy redshift 6. It's already a factor of 10 higher than globular cluster in the local universe. What we see then again is that a few of the star cluster are now sitting in a region and playing the game of medium and broadband. We can actually estimate that in this region, the equivalent width is thousands. So we have a very extreme burst episode happening in this region, driven by star cluster. And then finally, I think one of the most, I think this is the redshift break, the redshift record so far, but I hope we will find even higher, maybe not. We were looking at this object, SPT0615, this galaxy cluster. Here you see the lensing model. And in this region, close to the cross-seek line, we actually see the light of a galaxy. This was already an JWST candidate. It was quite bright in the infrared WPIC3 data, so it was already known. But with the JWST data, what we see is actually a very high redshift arc. So we estimate a redshift 10 for this object. And then we see also symmetries, which will come out in the next slides. But so essentially the critical curve is crossing the arc. We see even faint tails with the clumpy light distribution, which we couldn't study. We know so this is the prediction from lens model, and this is where is the candidate, which we think is the counter image of this arc. Sorry, this is a redshift estimate of the galaxy, so we don't find the secondary peak. It's quite tight around the redshift 2, but we have not yet spectroscopic confirmation of this redshift. So when we look then at the light, now you see in this image essentially the symmetry of the object. We see the caustic line is crossing here the arc. So we have a very high magnification, which are going down to 50, a factor of 50 when we reach roughly this object. Here you see different model, and of course we have looked at them. So cluster A is the most distant. This is a source plane reconstruction of how these clusters are distributed. They are within a region of 50 parsec. So this is quite amazing because these 5 clusters seems to have a mass of 10 to the 6 solar masses. So imagine the density of this little region, 50 parsec across in stellar density. The star cluster produces 60% of the UV light of the galaxy. The galaxy has an absolute UV luminosity of -17. So it's like a dwarf, a faint dwarf, a redshift 10. And it hosts a 5-star cluster within them. And the mass is roughly 30% of the total mass of the galaxy. So here you see some of the data. for both the galaxy and the cluster. Ages, we derive ages that are roughly 50 million years for the oldest object, which seems to be E, and then it becomes slightly younger, with A being the youngest of all. When we look at stellar density now, so this is really telling. So here you see the sizes and surface stellar densities. This cloud, the pink cloud, are the local young star cluster in the galaxy I showed at the beginning. And there you see this is like the median mass of this cluster is 10 to the 4, and they are sitting in a stellar density of a few times 10 to the 2. While the gray dots here are the globular clusters. So we know their median mass is 10 to the 5 solar masses, and they have a density of a few times 10 to the 3. And here you see now a collection of the cluster I showed you in the sunrise. I didn't show the sunburst arc, but it's also one of these arcs highly magnified where we can see star cluster. And what we see in general, even with high uncertainties here, is that these clusters are reaching easily 10 to the 5 in surface density. So this is really impressive. So we haven't seen such stellar density on average. But what we think is happening is essentially you expect them to be much denser and compact if they get an ample time to essentially expand. There will be stellar evolution, so they will lose mass, they will expand because of that. There will be also relaxation effects. There is N-body through Hubble time taking place. And then there will be stellar black holes, which will actually increase these interactions. If we also try to speculate, essentially when we look at these stellar densities, then what we know is that we for sure these star clusters harbor very massive stars. And in the local universe in 30 Dor, we are looking at stellar masses of 300 solar masses, and it's not even a very low density environment. So what happens if you do then run N-body with this stellar density is that you can easily produce a very massive star, or this supermassive star. You can reach up to 1,000 solar masses in stars in the core of this star cluster. And you can have a runaway black hole merger. So this becomes then a viable channel for growing intermediate mass black holes. And for instance, this is really important if we put in the context of the properties of galaxy that we are seeing at redshift 6 to 9, where we see, actually even 10, where we see a nitrogen enhancement with respect to oxygen. And if you remember, this is also where globular cluster enter in play. We know the globular cluster are sitting here when we look at nitrogen over oxygen abundances in their stars. So we see galaxies, very compact, bursty galaxies, similar to the cosmic gems arc that have this nitrogen enhancement. So again, a link to globular cluster in the local universe. And of course, I know this plot is a bit tailored to GNZ11, but what I like of this plot essentially is showing that globular cluster could actually be a channel for the formation of all the AGNs we are seeing within galaxies. Because if you imagine this 5-star cluster within 50 parsec, it will not take long for them to merge in the center of the galaxy. And in fact, simultaneously to the publication of the Cosmic Gems work, people were actually funding this. So this is like isolated dwarf galaxy simulation, where they look down to parsecs, to sub-parsec scale and stellar masses of 10 0.5 solar masses, and then they form, you see, these are a little compact star cluster within the simulation, and therefore they follow the N-body of the stellar black hole within them, and they see essentially that this object within 50 parsec are emerging. And in some cases, the black hole is staying in the star cluster. In some cases, is ejected. So the point then, if we want to look at black hole growth within high redshift galaxies, intermediate mass black hole, is to answer the question, will they stay, will they go, and how then later on they will be fed to grow to become supermassive black hole. I'm really late, I'm sorry. But yes, this is the summary essentially of the second part. We see stellar clump physical property to become very dense, very extreme. Clumps are becoming younger. These are the regions where globular clusters are forming. And when we look at the very high redshift, we see even, so for the few examples we can resolve to see proto-globular cluster, we think essentially that they can actually harbor the seeds for intermediate mass black hole and very massive stars to create these nitrogen enhanced galaxies at high redshift seen by JWST. And I will stop here. Thank you very much.
Thanks, Angela, for a great talk. Do we have questions for Angela? One here.
Yes, there is an analogous situation with massive galaxies in the early universe. They are also very compact, very luminous, etc. Is this simply the reason for that is the increasing density of gas from which these clusters and galaxies are formed ultimately?
I mean, those galaxies looked like scaled up vision of a star cluster. So it may be that the starburst that created those galaxies was much higher, and essentially you created all the mass in those regions. It could be that they form star cluster. Essentially, what we lack right now is an understanding from theory how these very compact galaxies, a few tens of parsec, form star cluster and how they will evolve, right? So object, more you merge, more extended the galaxy will become. So these very compact post-starbursts that are found at redshift 5, at redshift 6, they must have formed really fast and not through many mergers. Otherwise, they would be much more broader. It's difficult to make the link with the star cluster. I think what we can explain is the very high star formation efficiency that could explain the very bright galaxy at redshift 12, 11, 10. If it's due to star formation, it's probably because within them, they've formed many star clusters. If this galaxy could do it, I think that the GNZ11, they say there is a black hole, but there must be a lot of star cluster within them. It cannot be only a black hole. Yeah.
Yeah, another question. It has been claimed that by observations that black hole feedback can induce star formation. For instance, the famous Minkowski object and many other examples. Would for instance, the massive stars or clusters formed in the Minkowski object due to black hole feedback, jets and so forth, will be something basically different from the clusters formed just by gravitation?
I don't think so. So if the feedback from the black hole will be positive, it still has to compress the gas will fragment and turbulence. So I don't expect the star cluster to be different. It might be that the masses will be different in terms, the black hole will cause higher turbulence. So before that can collapse and form cluster, maybe they be like more massive. You will not see the low mass end because it's like in the center of the central molecular zone in the Milky Way. We don't see low mass cluster because turbulence is too high. So the black hole feedback may drive higher turbulence, but then if you have a lot of gas, you may overcome and then still collapse, but then you will form a very massive cluster. I mean, it's a bit difficult to extrapolate from like what we know, what will happen. It will be easier to see it via models, including all the physics that can reproduce the observation and then look at the black hole feedback. So it's a good question, but I don't have the answer, essentially.
Thank you very much.
Thanks, Angela. Going back to the first part of the talk about the characteristic mass of the cluster mass function, do we have any physical understanding on where it comes from? Is it connected to the, the characteristic mass for the IMF, or like, what's the physics that's driving this mass? Maybe, I guess.
Yeah, I think it is connected to the molecular clouds mass. So molecular cloud, the maximum mass that you can reach is also connected to molecular clouds. If we assume the star formation efficiency is 1%, then you expect molecular clouds of 10 to form a 10 to the 5 at 10 to the 7 solar masses in molecular clouds. If star formation efficiency changes, then and we can have a higher star formation efficiency for massive cluster. Then,
so you're saying that it's like just the amount of gas available that's creating this exponential cutoff?
Yeah.
So it's not feedback and dissipation with turbulence, any of that?
It's a dynamical time scale. It goes back to the tumor instabilities, essentially. Yeah.
So Angela, that was great. I enjoyed very much your very pan-epoch view of these small objects. So I would like to first make a comment and then I'll ask a question. So my comment is about the intermediate mass black holes. So this is a fascinating topic. And the problem, there's always the worry that globular clusters, it's difficult to grow an intermediate mass black hole because you have a lot of mergers. And unequal mass mergers will just drive it away, all right, with a kick velocity from the anisotropic emission of the gravitational waves that carries linear momentum. The merger will have an opposite linear momentum, and it will be kicked out at a speed well above the escape velocity from the cluster. It might stay in the galaxy, and even that is probably not sure.
Thousands of kilometers per second.
Yes. So it's very difficult to grow an intermediate mass black hole. So that's why I'm dubious of the discovery in Omega Cent by Heberle, as well as my own in Messier 4. We were very careful about that. And
I think you are right, and but this is because most of the work has focused on density. So if you look at globular cluster density today, which is 10 to the 3 solar masses, all the black holes are kicked out, and I agree with you. But if you look now at the recent work where they are looking at higher stellar densities, so the number of particles go up to 10 to the 6, 10 to the 8, then there is a chance that the black hole can grow inside.
Because the escape velocity is much higher?
No, because it happened, yes, because the escape velocity is much higher. So there is a higher chances when the density are really high that the black hole can stay. It's still, I wouldn't say 50-50 even, it's still 20-30%, but there is a chance that it stays. And then of course, the problem is, will it be ejected from the galaxy? So you are right there for those who are ejected, what happens? Yeah.
Okay, so my second question is, I know much better the universe at redshift 0. In fact, I'm very afraid to get out of there. Okay, and so we know that the distribution of galaxies in the size-mass relation is kind of bimodal between one branch, which is the compact ellipticals like M32, the ultra-compact dwarfs, and the globular clusters. They seem to form one sequence, And there's another sequence, which is the dwarf ellipticals, the dwarf spheroidals, okay, which are much puffier. And one wonders, what are the conditions to make this difference? And also, and related to this question, and related to, I think, the first question of Felix, is that so the globular clusters that you're talking about, are they the same objects as the compact ellipticals or ultra-compact dwarfs? And so we tried to look at this in simulations, which were probably not well resolved enough, and we're probably missing physics. So, you know, you have to take a grain of salt of this. But we found that we ask ourselves, what makes the compact galaxies so compact? The ones that we pick up at redshift 0, because that's what I'm interested in.
Yes.
And we find that they're the lucky ones who live, the ones that end up as centrals. Okay. They're the lucky ones that grew in halos as centrals that were lower mass and which had fewer satellites. And so they're the only galaxies that did not have sufficient mergers before redshift 1 to prevent angular momentum coming in from the mergers, pumping inside. So they're the only ones that have gas inflows. And the gas inflows drive star formation inside. So that's what makes them compact. Now, this is the simulation, all right? So I think what you're showing is completely different, because you have the resolution to see the H2 regions at these different redshifts. And so it seems like completely different physics.
But is it? I mean, if you have in 50 parsec 5 object of 10 to the 6, dynamically they will merge, right? And they and they have a sizes of 1 parsec. So even if you merge them, they will become 10 parsec, a nuclear star cluster.
Yes, you have a compact group of star clusters.
Yeah. So
Yes.
yeah. But yes, I know that there is a lot more literature and evolution to explain the compact object. This is just trying to understand really what is happening in this early galaxy, right? Yeah, what do we see?
Yeah. Thank you. Thank you, Gary. You used all the time available for questions.
Okay.
So, yeah, we can discuss, of course, with Angela. She's here the rest of the day.
I'm still here, yes.
Thanks, Angela, again.
Thank you.